Greetings, Earthlings. Well, my transistors have arrived, so I guess it's about time to replace this thing and see if we can get that power supply working again. But before we do that, let's pick one. We're just going to verify. These came, as I mentioned before, from Electronic Surplus, which is in Ohio, I think. I don't know. While I was at it, I may have mentioned I also got some 723s, which are the voltage regulators, in case I need it. But let's verify this with the diode checker. Just because the other one we saw was bad. So it's emitter-based collector. And it should look like a diode in one direction and an open circuit in the other direction. So that's looking like an open circuit. That's looking like an open circuit. Okay, let's swap the leads. That looks like a diode. And that looks like a diode. Okay, so that transistor looks like it's working okay. There's the heat sink. I'm going to mount it on the heat sink, and I think I'll give it a little smear of silicone thermal compound, which I don't think the original one had. Let's have a look. Right. No silicone grease there. Okay. I don't think that's what caused the failure. But since I got it, I'm going to put that on there. All right, a little bit of that. Little dab will do ya. And we'll get that together, and then I should bend the leads. And then I'll get soldered back in to the board, and we'll pick it up from there. All right, and here's what it looks like with those parts changed. I don't know. I don't think I showed you the replaced resistors. Here are the resistors and the capacitors. And then here's the new transistor in place. These resistors, I stood them off the board. The originals were hard up against the board. They don't really look like they get really hot. Because the board's not discolored, but it makes sense just to stand them off the board just to be give a little more air circulation there. I'm going to turn this over, get ready to plug it in. Let's see. Actually, we want it around this way. I think this goes here. Okay. Just want it standing off a little bit here. Give something to support the board. Again, I have a suspicion that one of the op amps is bad, and so I'll probably need to be making more mods on the board. Oh, and I want to replace those wire ties. I don't know if you noticed. But it doesn't use proper cable ties. As I pointed out in the very first video, they're like sandwich bag twists. They're just wires, you know, with some sort of plastic coating on them. So here are all my test points, and I'm going to hook the, let's see, hook the meter back up. All right. And I need to plug this in. Actually, I need to turn it on. Where's this control here? There we go. Okay, you can see the neon bulb. Maybe you can see that here. Neon bulb is lit. So, now then, as we determined previously, test point 19 is plus 5 volts. We had a 19A and a 19B. Here's 19B. 4.86. I like that. 19A. 4.86. Okay. Okay, and there's test point 30. And we can see it's still is not 1, 2, 3, 4, 5. It still is not even, it's more so maybe than before. I don't know. So upward stair step, that's the input to the inverting amplifier here, or buffer. If I look at the output 29, okay, what we see is an attenuated version of what we saw previously. But it's not inverted. And that tells me that that op amp is not inverting. Can you see that? So IC5, I claim IC5 is bad. Increasing stair step. Increasing stair step. No inversion. And this, I mean, this is interesting, but again, not linear steps. And that would be because the signal is traveling through these resistors from here to here, and not being inverted and buffered by this. That's supposed to be a feedback path. So I'm going to change out that op amp, and I'm going to put a socket in there. And we'll see what that looks like. All right, and there is the replaced op amp, IC5, in its nice socket. Now, you say, well, gee, it didn't have a socket originally. How do you know that's not going to cause problems? This is real low-speed circuitry, so I really don't think a socket is going to cause any issues. It adds a little tiny bit of capacitance, you know, but it shouldn't matter because it's such low speed. There's a wire ties I've been talking about, and so I'm going to use proper bright green zip ties to replace those and get those done. So the thing now is to, well, we'll go and recheck those. We'll recheck those test points. It turned out that support wasn't really doing anything, so I'm not going to put it back. And now, what were those test points again? $29 and $30. All right, there's 29. It's different. For sure, that's different. DC offset. Oh, that looks like a nice stair step, and that's stepping down. 30 is, well, I don't know what it is. There it is. 30? Oh, I see. 30 is just one bit of the digital to analog converter. So there really isn't a proper test point. I know 30, 31, 32, there really isn't a proper test point for the inverting input of the amplifier, but 29 is its output, and as we can see, that now looks proper. So at this point, I'm tempted just to put it back together and run it through its tests, which may mean I'll have to take it apart again if I find another problem, but I'm hoping that's the only one. So I'll get those zip ties in and I'll get it all back together and buttoned back up, and we'll see if we can get it calibrated. All right, so here we are with the calibration setup, attempting to adjust the vertical. Now, again, they want 10 divisions vertically, and we only have 8. And then you're supposed to set 1 dot every 2, just to make sure that it's even and everything. I'm going to set them every 1, see if I can do that. So there's 6 dots, and I should be able to, yeah, that's pretty good. So 1, 2, 3, 4, 5, 6 every 0.1, or every 1 division. Okay, and here's the completed unit, all buttoned back up. Now I did, off camera, I did go and replace that voltage regulator. So the plus 5 volts is dead on 5 volts now. I also replaced those 2 resistors. The, what were they? 25K and 50K, just because I had them, just because I could. You know, to make it, get it as spiffy and accurate as possible. When they built it, you know, they spec'd 1% parts, in some places 5% parts, in other places they were building it to a price point and didn't have the luxury, shall we say, of hand selecting parts to get it better than, you know, they spec it plus or minus 3%. Well, I do have that luxury, so I took the opportunity. So let's take a look now and watch it do its stuff. I cleaned these sockets up a little bit with some deoxit, but they still seem to be a little flaky. Here's one of those 4.7K resistors. It's a metal oxide resistor hello. Like I said, it's still a little flaky. Oh, wait. Let's try that. Yeah. That's looking like a resistor. A very boring resistor. Where does that? That should be there. Okay. But a resistor nonetheless. There we go. Okay. Straight line. Really, resistors are boring. Let's look at some diodes. Okay, I have 3 different types of diodes here. This is a 1N4004. And you can see there, it looks like a diode. Okay, that's, there you go, 0.1 volts per division. So 1, 2, 3, 4, 5. This is 0.6, so somewhere between 0.6 and 0.7. as you'd expect. And of course, in the other direction, it just looks like an open circuit. You just get a straight line across there. Okay. Oh yeah, even if I switch it properly. Okay. That's a diode. This one is a Schottky diode, Schottky barrier diode, SB160. So we'll see what that looks like. Oh, it looks like a diode, but there we go. 0.1 volts per division, so 1, 2, and it's about 0.25 to 0.3 volts. Almost like a germanium diode. Oh, and again, reverse biased. Reverse biased, it doesn't look like anything, you know. Yeah. Okay. It's 60 volts, and I can only go up to 50 on the display here. That's max out because I'm not using a times 10 probe. So we can't see it break down. However, I do have a Zener diode, and this is an 8.2 volt Zener. So we're going to try that. Okay, this is a forward bias, so it should look like a regular diode. Yes, it does. And let's see, 1, 2, 3, 4, 5, 6, 7, between 0.7 and 0.8 volts in the forward direction. But much more interesting, because this is what it's for, why you buy it, is the reverse direction. Oh, look at that. Okay, 8.2. So 1 volt per division. And on the vertical here, it should be, it's about 1 milliamp per division. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7. Let's go, 8 milliamps. It's still not quite at 8.2. I don't know what it's spec'd at. This will be 2 microvolts per division, or milliamps per vertical division. I think we can get it to, this is 5. We can get, I don't want to overdrive it, but we can get it to 8.2. There's about 8.2 there, you see. Yeah, right, okay. Actually, if I put it there, that's about 8.2. And that's 5, 10, 15, at 20 milliamps. Okay. So that's fun. Okay. Transistors. Here's one of the D40D1s. It's emitter-based collector, so it goes in this way. It goes in backwards. And I'm gonna have to wiggle this a little bit to get the. Oh, there's the curves. Okay. And that's what a transistor looks like. That's an NPN. Here's another NPN. This is an old. I don't know what this is. Because it's got a lambda power supply. This is a spare part for a lambda power supply. With a 1986 date code. FBN L109. Okay. Whatever it is. Okay, now. On these TO5 cans, you have a little tab. That's the emitter. And then you see the case here. Those are insulated. And this lead connects to the case, so that'll be the collector. And so it's emitter-based collector. So it goes in like that. Come on. Oh, there. Okay. Let me go down. Okay. That's a nice looking curve. You know? Yeah. That's a nice looking curve. Okay. Whoops. Okay. I have a power transistor. This is an NPN. This will require leads. Let me grab a PNP. Okay, this is a BC327 PNP transistor. So I'm going to switch to PNP here. Okay. It goes in, let's see, it is collector base emitter. So it goes in just like that. You know what? I'm going to try it in this one. Just to see if this socket works a little better. Now what happens with the PNP is that we have to, it comes down from the top. So we've got to go up there. Okay. PNP, and let's see if we get any curves here. Let's put it down there. There they are. Okay. There you go. That's what a PNP looks like on this curve tracer. So let's do this power transistor. I don't have proper colored leads, obviously. The long one's the collector here. On this is, again, out of that Lambda power supply, L198, but it's really probably a 2N3055. That's the collector, the case. Now, which is the base and which is the emitter, I can never remember, so I'm just going to hook them up. If it doesn't work, it'll be obvious. That's NPN, okay. Oh, and so it's NPN. We need to go back over here. Okay. And let's see what we got. Nothing. Okay. We'll try reversing the... Oh, wait. Let's try it again. With the switch in the right place. Oh, I got it right. Okay. Ooh. See how it's kind of loopy there? That's, I think an indication of high capacitance. But this thing is meant to operate at higher current, so we're going to crank this up. Yeah, see. That's more in its operating range. That's a power transistor. So that's pretty happy. Okay, so I'm going to call this working. I may fiddle with it some more if I find myself a nice 12.5 k ohm resistor to put in that digital to analog converter. And I'd really like to find a different oscilloscope to use with it. This one's too useful for regular stuff. I kind of want to have one dedicated to it, so I can just have this set up on a bench somewhere, for ready access. And I'd like to have an oscilloscope. Doesn't have to be a great oscilloscope. It doesn't need, this is 100 megahertz bandwidth with a built-in frequency counter and a digital multimeter in it and stuff. Like I said, it's just too useful for normal everyday stuff. Also, I'd like something with a bigger screen, But the bandwidth requirements are minimal. It just has to operate in XY mode, so we'll see what I can find.